Okay, so the first homework was change the loading to uniaxial tension. So to do that, I'm at the plasticity folder. So first I need to cd plasticity applications, crystal plasticity, FCC. And the example we solved yesterday was FCC random orientation block. So first I will remove the results from yesterday's simulation, but I will open the boundary condition file. Oh, sorry. So here in the boundary condition, the direction of displacement is negative, which was compression in our last simulation. So today I quickly will change it to tension by removing this negative. So this will be the displacement at the end of simulation time. Considering the sample size, which is unit, it will induce 5% tensile strain. So let's start. Let's check also how frequent are we generating the output. So every 25 time steps, we are printing the outputs. And this is pretty much, the time step is the same. The material is still copper. And it's 5 by 8 by 10. Each grain is modeled by one element. And that's it. So we can start the simulation by typing MPI run -n. I'm using 6 processors. If you don't have 6 processors, use less. If you have more, you're free to use more processors. So it will be main. Okay. So I'm going to kill this after about 50 increments. So I at least generate 2 output for visualization. So we are expecting this one to be uniaxial tension, unlike the one that we did yesterday with which was uniaxial compression. So it should be finished in a minute, but what's the next problem that we are going to solve? Refine this problem further. And because if we refine the problem further, we will have more finite element mesh, more refined finite element mesh, and more number of elements. The simulation will be slower. So I just will change the skip output steps to 1. And after 1 increment, I will kill the simulation. So in that case, I'm just going to post-process it and show you how the refinement will change the mesh size. So let's go back to this. It's 35. So we need about 15 or 14 more increments. And after that, I will go over output quadrature output and investigate the output file with just grain ID and position. As I mentioned before, the default quadrature output contains many parameter files, but I'm gonna do just as an example, comment out all of those, compile it, and just output as quadrature output, just the position of the integration points and the grain ID, and see what happens. So that would be our next example. Okay, very good. So I'm just killing this by Control-C. Then I will open the ParaView. So I will go open. I will go results. So this is not the one. Ours is in test, plasticity, application, crystal plasticity, FCC random orientation block, results, and I will open solution. So then I will make it to U deformation, and that's along Z axis. So you can see this time we have positive value of deformation along Z, which is uniaxial tension. So if I just go filter, wrap by vector, or you can go alphabetical and find it as the almost last filter, and then apply, and then scaling it up to maybe 10, and then make it surface with edges. Then you can go forward and you can see how it deforms. This is the first one. This is the tension that you're actually applying. You can make this like 30 to becomes more obvious. So this is the first time step and this is the second time step. So this is pretty much how you change the deformation from uniaxial compression to uniaxial tension. In the next homework, what I assigned is make it finer and make the number of output faster. So because the simulation is slow, we cannot wait 50 time step. So to do that, what I will do is I will go open PRM file, and I will first add set refinement factor and makes this 2. And then what I will do is I will set the skip output equal to 1. You will see that the simulation will be tremendously slower. First, let me close this. Oh, something else that actually you can do is you can plot the stress strain to see how does it change when you actually change from the uniaxial compression to uniaxial tension. So you can go browse, you can go download, test, plasticity, application, crystal plasticity, FCC, random orientation, and make this all files. And then you have stress strain. So make finish. Then you can plot EZZ versus, this is the along Z axis, and then insert. So this is tension. So now you have tension along Z axis. Okay, so this is a stress strain output. So now let's close this. Let me remove this results and run the new simulation. This simulation will be much finer. It has 25,000 elements, and using 6 processors, it will take some time to do even one simulation. Hopefully, okay, since the first simulate like steps are almost elastic, you can get away with a faster time step. So with a faster runtime for the first time step. So we'll wait until the first. Okay, now it's done. So now if you go and open recent, actually you can use open, and you can use solution, apply, and if you just go surface, you can see that the F image becomes much finer. So this is how you actually refine the sample and make it the simulation, but it definitely makes the simulation slower. So the next example homework that I prepared was changing the output quadrature and just printing out grain ID and position. To do that, you can do it either via VIM or any text editor you feel comfortable. I'm using usually Atom. Excuse me. So what I will do is I will go test, source file, material models, crystal plasticity, and open update after increment. This is pretty much about the main activity you're doing for after your time step is converged and you just want to process the data and make the output for the visualization or any other purpose, you're using this. So if you want to just print out the quadrature output positions and grain ID, this is the grain ID, cell orientation map cell ID. This is phase, we don't need it. This is the Jacobian of element, which is 1/8 of the element size. In the case of linear element, we don't want it. This is if it's twinned or not, we don't need it. These three are the position of integration point, we need it. And then you can comment out the rest. That's a long list. Because there's like a default. If someone wants the most, so you can comment that out. And then here as well. And here as well. And this as well. This is the last one, I guess. So this, you don't need it. So you should decide what kind of quadrature output you want for your simulation set. What I'm usually do is for a specific application, I'm come up with, okay, I just need this specific set of quadrature output. I build it and I just compile it once. You don't have to change it all the time. But this is like basically changing once you are reusing the simulation. And you're save this. And now you go back to your simulation. Now you need to recompile it. So you go to the PRISMS-Plasticity folder, which is 2 folders above that application, and do make release. Now be careful. It should show that the update after increment.cc has been modified here. Unless it shows that, it means that your recompiling doesn't work appropriately. Sometimes when you're using the same file name, okay, you can see now here, it says 1% update after increment.cc. So it means that this file change has been recognized. Sometimes when you're copying the file with the same name and substitute it with the older one, and you recompile it, you can see that it cannot be correctly recompiled. So you need to either delete that file for a moment, recompile it, get the error and recompile it again, or just do a complete recompile, which is like deleting all the CMake and make files and from the scratch. But I'm usually just moving that file and get the error first, make sure that it recognizes the deletion, and then move back the file that I just want to have. In this case, you can see it recognized our change in update after increment. So we're good. So after this recompiling is done, I'm going to add the quadrature output to the file that I've just modified to make it refine and see how it goes. So hopefully this will be finishing soon. But to save some time, I just will directly go and modify the file here instead of VIM. So I go to PRISMS-Plasticity, FCC random orientation block, parameter, PRM. And then here I make this refinement back to the default, which is 0. And if you go to the handout, there are 2 lines you need to add. Set refine factor to 0, set skip output to 25, and adding these 2 to the simulation. So you will have making this back to 25 and adding those 2 lines, which is set right quadrature output equal to true, which allows the code to output the quadrature output. And the next one is how frequent that output will be generated, which is in this case similar to the visualization, which is 25. So we are good. Now we will see how the, okay, I think it's done. Okay, now I can go back to that folder. which is random orientation block, and then remove the result folder, and then just run the code. So here, I'll just wait 25 increments, and after that, I will see the only quadrature output. If I wait like 50 increments, then 2 quadrature outputs would have been generated. So for creating a finer mesh as it's advisable, okay, to increase the number of mesh subdivisions by keeping refined, or simply increase the refine factor or constant set of mesh subdivisions. So for that, Aurel, what you need to do is, in general, using set refinement factor is it's wiser, because it put less load on the FE system. There is some memory reasoning behind that. But in some application like periodic boundary condition or element deletion application, you cannot use set refine factor. So that might be one of your limitation. Another one is if you want to use a 36 by 36 by 36 mesh, then there is no not 36, maybe for example 7 by 7 by 7. You cannot refine that at any way by set refine factor. So then you have to go with the subdivisions. If it's neither of the cases, it's always better to start with 1, 1, 1 with subdivisions and use set refine factor. Okay, sure. So I will cancel this simulation for now, and then I will go and see the results. So if you see the results, you can see there is a new file here, quadrature output 24. This quadrature output 24, it's because it's outputted at the increment of 24th. So if I open this, if you generally generate this file, it's a very crowded file. But just now, let me change the format of this. It's just general. So the first column here would be grain ID. And the next 3 would be position X, position Y, and then position Z. So this is what you actually define in update after increment file and recompile it. So this is how so if there is any other variable you want to actually output for each integration point, last session we had a question regarding if someone is trying to average the stress in each grain, what should they do? The handy way to do that is just to output quadrature of those integration points with the grain ID and that a specific stress component you are interested in. And then you will end up with either 2 columns, grain ID and the stress. And then you can easily post-process that with any MATLAB, simple MATLAB script codes to average the stress within each grain. So there are infinite possibility to post-process this file. So this is an important file. So this is basically how you modify your quadrature output file. So what if you want to add another variable to the visualization? This is another important aspect. For example, by default, if you open a file in the ParaView, if you open one of the projects, so you get even either nodal displacements or you get the projected fields, which in default it's it's solid color. Okay. So it's either equivalent stress, equivalent strain, mesh grain ID, which is grain ID. And this is subdomain is actually what processor solved this. This is really nice. It shows what processor solve each of the grain IDs, each of the grains. But besides this, you cannot generate any other variables automatically unless there is a way to do that. So again, the question in the handout is how you can add TZZ, the Cauchy stress tensor component along the ZZ direction normal is basically sigma ZZ or TZZ, depending on your name or label you put. So for that, you need to again open the update after increment.cc, which I have already opened it. And then there is a part here that after von Mises, which is equivalent stress, equivalent strain, and tween, there are a bunch of parameters that it's predefined as 0. If you want to add anything to the visualization, because remember, visualization is not easy process. Either you need to predefine whatever you want, because you have all those variables at the integration point. So you want to have them as a nodal point to post-process it with ParaView. So you need to solve an inverse linear equation. So what will happen is you need to add that component. In our case, we want TZZ. In the code, if you read the manual, T is the Cauchy stress tensor. And if you just grab T here and put it here, and then define 2, that would be TZZ. And then that's what you need to do here. Then, again, this is something, what I would suggest is for whatever system you have, just come up with your best and optimized parameter or variables and just do this once, because you don't want to recompile the code. So this is like, you figure out for your problem, these components or variables are important. You just add this according to this, and then it's very simple to add it to the code. So you just need to recompile this again. So we go 2 folders above to crystal plasticity and make release. Again, you should be careful. You should watch that change should be recognized by the compiler. So you should get 1% or some percentage with the update after increment.cc here. Here again. So you got this line. So another change you need to make while it's getting recompiled is you go to parameter. If you open your handout, you need to add this line. Set output variable 1 equal to true. When you have set output variable 1, this corresponds to the first line after tween output. So there is a header, user defined variable for visualization output, output var 1 to output var 24. So there are predefined 24 of those. So the first one belongs to this. So when I will say set output variable 1 equal to true, it means that add this to the default values. So I will just copy this and paste it here and then save this. And let's go back to see if its compile is finished or not. Okay, it's almost done. So after it gets finished, I will rerun this simulation and show what ParaView will show. Okay, it's done. So it's FCC, it's random orientation block. I will remove the previous folder and run the simulation. Okay, now we need to wait another 25 increments. And then we'll open it with this. So I will just first. So again, you can see here we have equivalent strain, stress, mesh grain ID, and subdomain. That's it. So I will just delete these two, waiting for simulation to get done. So is there any question so far regarding these features? Okay, it means I'm doing a good job explaining this, or no one understand whatever I'm explaining. Okay. Okay, we got there. So then you can just simply go and open. When you open the project field PVTU, then you apply. Now you should get output var1. This will be your TZZ component you just defined. So this is how you add extra variable to your post-processing, if it's not the default variable. But still, if it's some like statistical analysis besides visualization, you can always use Quadrature output because it will give you the precise value at the integration point. This is the post-process value prepared for ParaView by inverse solving that linear equation. So the next step is, and again, last session, we generated a random microstructure using default Dream3D. Now today, we want to start with an eBSD file, like load from bulk file, and actually use the generated grain ID and orientations.txt. To do that, we are opening the Dream3D and click on this, and we are going to plasticity, training materials, pre-processing, this time FCC, and Prisms pipeline FCC. So after we open this, oh, why T22? Because the C++ starts from 0. No, it's set output variable 1 equal to true is actually, you will just get that one defined. If you want to add another one, you need to set output variable 2 equal to true. And for example, add T11. That's how it works. Each flag belongs to just one variable. Okay. Now, here, we're not going to change the crystal structure because it's already cubic and copper. So for the ODF part, we're going to click on bulk load from file and select the training session, plasticity, training materials, pre-processing, FCC, and copper data 1. This is let me open the copper data 1 first. So this is pretty much similar to what I showed you before. This is like cut from an eBSD map. It has 399 grain ID, and the first 3 are you can see these are the radians and Euler, Bunge-Euler angle, and these 2 is just 2 columns of 1. So if you close this and select copper data 1, and then click on load data, you will get your pole figure, and you can refresh this. Okay, and load data. Okay, and you can also plot this using Lambert, which is colored. And load data. Okay. So this is generating, you can see a random texture from an eBSD which had a random texture initially. And then you will just create data. Okay. Now check the estimate. So the estimate number of features are 315. The number of voxels are 32 by 32 by 32. So it's good. It's 315. Maybe you want a little bit coarser, finer grain. So let's try 20. No, sorry, 5, 5, 5. This is only 28 grains. but it's very refined. And the dimension is 32 by 32 by 32. So you need to update the addresses again. Paste again here. Yep. And here. So then you can click on Start Pipeline. So after it's done, you don't need the Dream3D. So you can just discard it, and this can go down. So then you can go and check the folder actually. So it's plasticity, training, pre-processing, FCC. So if you see date modified, it's like 3:32 Eastern, which is right now. So these are the sets of the file that has been generated. And the grain ID, if you open it, you need to open it first to see how many header you have. Typically, with this pipeline, you always will end up with 20 lines as a header, and the number of voxels are 32 by 32 by 32. These are the important information you need to have. So what you will do is, okay, so we're done with this page. We're done with this page. We did this one. We did this one. We did this one. Okay. The two outputs are grain ID and orientations. And this is the information we generated out of it. So the next part is we generated these files. But let's move on. Rather than using rate independent crystal plasticity, what if someone wants to use rate dependent? Actually, I myself personally always rather to use rate dependent because it gives me some flexibility the rate independent models generally does not. So what would you do if you want to actually start using rate dependent model to model the microstructure you just created? So first, you can actually see what microstructure you generated. So you can go to FCC, copper, and said okay, and apply. So this one will be feature ID and surface. So you see, this is a pretty coarse grain ID. So we choose only about 20 something. It has 31 actually. You can see the feature ID, the maximum number. So this is the microstructure we are going to model using rate dependent crystal plasticity. So to do that, first, what you need is, you need to go to folder above. Now you are in the crystal plasticity. You go to source, material, crystal plasticity. You can see there is an original calculate plasticity, which if you open it, which if you open calculate plasticity, it's the rate independent model somewhere. Yep, this is Anand and Kothari, 1996, which is a rate independent crystal plasticity. So if you close this, then there is a folder here, material models. This material model folder include all the implemented material models so far in PRISMS-Plasticity. All the information will be added to this one. So what you will have is you can copy from that material model and go to rate dependent model. There will be two files there. Calculate plasticity and user functions. The calculate plasticity.cc will be your main file, while the user functions.cc is all the auxiliary functions you're using in your user subroutine implementations. So I'm just copying both in the calculate plasticity. in the crystal plasticity. So now if you open calculate plasticity, you'll see that this is rate dependent crystal plasticity model. So here you go back to your applications. Oh, one more. Crystal plasticity, and now you need to recompile the code. Be careful, sometimes when you're recompiling, since the name of the files were similar, it doesn't actually get the new file. So you need to see that one line, it says the calculate plasticity is updated. So we do make release, and let's see what will happen if we get that line or not. Okay. Oh, here we go. We get that. We got it. Okay, 1% calculate plasticity, and after that, it should be user functions. Okay, until it will recompile, I'll just go over what are the next steps for you. So we did make release. It will give you it. Okay, this is a procedure I use as a bypass if it doesn't recognize my changing the file. But in our case, now it worked perfectly, so we don't need this. So you don't need to follow this part, essentially. So the next part is you need to copy the generated microstructure of your grain ID and orientation.txt to this application. Plasticity applications, crystal plasticity, FCC random rate dependent. So this FCC random rate dependent was initially designed for 5 by 8 by 10. Each grain is modeled by one element, but now we want to modify this. Let's see how the recompile. Okay, now you can see there is also user function.cc here. So we're almost done with the recompiling. Okay. So let's see. There is no question so far for this. Okay, that's good. Or that's bad, I don't know. Okay, we're good. Now we want to go to the FCC folder and go to FCC random rate dependent. So if you go there, first the original grain ID is like this. This is like 5 by 8 by 10. So it's a pretty much simple grain ID. So we want to remove this grain ID and remove the corresponding orientations file. And then copy. So I will copy the generated grain ID and orientations, which I did it, I believe, in a few folder above. Hopefully I can handle finding it. Oh, yep. I have it here. Pre-processing, FCC, nope, FCC. Okay, grain ID, I have it here. So I just copy it, and then I have the orientation file here. Okay, now if you open grain IDs, then you have 32 by 32 by 32. And then your orientation file also will have 31 line because you have only 31 grains. Now, the fun part starts. You need to modify this input file. So let's open the input file with the Atom to make it easier. So if you go to test, Applications, crystal plasticity, FCC, and rate dependent, and then, okay. So if you go to your handouts, you can see what options we are going to change. So first, I'm going to change the FE mesh to 32 by 32 by 32. It will take some time for the simulation to be done because it's a much finer than 5 by 8 by 10, but let's do it. So this, I will do subdivisions 32 by 32 by 32. And then I will make this true to output the post-processing. Then I have the skip output of steps of 5. So I will output this every 5 increments. Then I have the total time and the delta t equal to 5 and 0.005. So I will go and change the delta t. So this is false, it doesn't matter. This is 0.005 for delta t, total time is 5. What else? Voxels in X, Y, and Z. Now you have a different macrostructure. So you will have 32 by 32 by 32 voxel size. You have a different grain ID name, which is grain ID.txt. The other one start with the capital. And then you have a header lines number equal to 20. And these are false, so you don't need to worry about it. So this is all the changes we made so far. FE mesh to 32 by 32 by 32, set output equal to true, and a skip output steps of 5. Total time is 5, delta t is 0.005. Voxels in X, Y, and Z are 32. And the grain ID file name is grainid.txt. The number of header lines are 20. So these are all the changes I have. So let's go back to the file. So if you go to the next step, we are using rate dependent model. The rate dependent model have some changes for material constant. This is the flow rule for rate dependent model. So you can see it has a few parameters you need to define. Also, there are 2 features I'm using because we implemented the rate dependent model as a user subroutine. So when we implemented that as user subroutine, I was using user material constants. So this will read the user material constants. If you have any other constant than the basic ones, you can pass it through this option. And if you have some state variables that you want to follow and track during the simulation, you can use this option for your new constive model. So these are 2 basic features you will use if you want to implement a new constive model. We use those features for rate dependent model. So these are if you go to the parameter file here, you will start with enable user material model true, enable user material model 1. This is because we had a multi-phase implementation. You need to define if you have only one phase, but still you need to define that for material model 1, it's true. Then we're not gonna use advanced rate dependent, this is not important. Then the set number of user material constant, we in general use 12 material constant within this rate dependent model. And the number of state variables, we were using 62. So these are the material constant we are using for now. So you can change this also to 0. So the first one is the reference sharing rate. The next one, M, is controlling how static or how fast you're applying the load. Like if you have a really small M, it's getting closer to rate independent formulation. And these 4 are for, because we are using iterative Newton-Raphson procedure, 2 loops inside each other. So there is a loop inside another loop. Each one of them has a criteria of error threshold. and the maximum number of iteration you will use for that problem. So in that case, you'll end up with 2 numbers for criteria and 2 numbers for maximum iterations. And the last 6 numbers are backstress parameters. So we don't have any backstress in this simulation, so I just put it 0. So if you go back here, this is almost what we have right now. And after that, it would be elastic modulus and everything else would be the same. So these are the changes you need to do, hopefully for, let me save this file. And then, so now the only thing, okay, we did that before, calculate plasticity and user function, and we recompile it. So now let's do the simulation within that folder. So if you open the, just to double check the PRM file, now you should have 32 by 32 by 32 true results every 5 increments. And the parameters, these are updated. And these are the rate dependent constitutive model parameters. And all the other parameters are the same except the input microstructure, which I updated. So I can just start running the simulation. I did every 5 increments, and this is, I believe, still in compression. Let me check the boundary condition. No, this is tension. So let's change it to minus 0.5 for compression. So this is like 5% compression. Now, let's see, we have everything. So we can just use MPI run. Okay, PRM.PRM. Hopefully this will work. This is much slower, I believe. So we need to wait until hopefully 5 increments goes, because the number of increments are higher, and the rate dependent code, although it's more stable because you're solving the Newton-Raphson exactly to get the threshold in the window that you want, but it's slower. It comes with a price. So let's go back to this until the simulation goes 5 increments. So let's go back to another concept. So as I explained here, if you want to implement your own user subroutine, then there are pretty much some information you need that you can find in this documentation. And we can go over this documentation briefly together. So let me just click this and see if it opens that. Yep, user-defined crystal plasticity material model. So it actually explains what are the variables inside the code as a general. So we are using 2 versions, converged, which are the final Newton-Raphson results, and iteration, which is the results for each iteration, which is locally converged but not globally yet. And you have the T and P, which are the Cauchy stress tensor and first parallel Kirchhoff stress tensor. And all the other information are here. So you can find all the information. And then you can use these 2 features, user material model constants, to define or pass the material you want through the input file, and then define your own state variables, whatever number you want, and you follow them. For example, let's open the calculate plasticity for, let's see how many, oh, it's slow. So we need to wait a little bit. So let's open the source material, crystal plasticity, calculate plasticity. So this is the file for calculate plasticity, and this is how it looked like. So generally in your file, it starts with defining the multiphase. It doesn't matter if you don't have multiphase, you don't need even have to this. So you start with defining what are each of these have, like predefining the variables, and then reading the material constant that you passed into the code, and then reading the previously converged state variables. So all of them are state variables. Converged means previously converged variable in the previous step. And then you will start reorienting, rotating the crystal structure to the global structure by rotating the elastic stiffness matrix. And then you calculate the Schmidt factor here, and then you will calculate. So those two loops that I was talking about, those start here, start nonlinear iteration for sleep. So these two, the first one is this one, the second one is this one. So these are two inner loops to integrate the crystal plasticity model you have. After that, you have everything. So you can just pass the information you have into the TNF as a tau, which means that you're done locally with the convergency. And then the last step is if stiffness flag is equal to 1, it means that if you are in building the stiffness matrix phase, you just need to have calculate the algorithmic tangent modulus. This is a little bit tricky part in all finite element plasticity code, not to mention crystal plasticity, which is a little bit more complicated. So the output of this will be this matrix, dp/df, which is partial p over partial f, which p is first Euler-Kirchhoff and f is deformation gradient tensor. So this will be your algorithmic tangent modulus to build the global stiffness matrix. So this is pretty much what you need. And if you have twinning, you'll have the final stage to define if your integration point is twinned or not. And that's it. Developing this file from the scratch is really hard. You need to have a certain set of skill. But if you have already implemented your crystal plasticity model in other structures, you can easily translate it to C++, especially since this is like open box. You can also compile it and debug it very handy. Unlike the other commercial software, you need to write a file actually to check some of the variables. You cannot debug it on the fly, but this will give you the flexibility to debug the code on the fly. If anyone is interested to transfer their UMAT or any other software like Nastran or ANSYS, they can reach out to me after the session. We can work together to translate your own UMAT into the PRISMS-Plasticity constitutive model. So let's go back to the simulation. Let's see. Okay, we have 2 increments out. So we're waiting still. This is because okay, I think in the handout, I print out 10 to power minus 4 to make the simulation faster, but I forgot to change it in my code. I think it's still 10 to power minus 6, which is harder to converge. That's the reason I got so much, it gets so much time to get converge. So if you use a smaller threshold, basically it takes much more time, but give you more stable answer. So it's an optimization you need to do before you start your real size simulation for your simulation system or special geometry you're modeling or special boundary condition you're trying to model. So what I will do is I will just kill this and I open the PRM file here and I make the output just one to make it very fast, and I make this 4 and 4. Hopefully this will be much faster. So this is a brief overview of what UMAT would look like, or what user subroutine would look like in PRISMS-Plasticity. So that's this part, we're done. So the next session, the next part that I will go over will be periodic boundary conditions. But first, let's see. This is some warning, but let me see if I correctly. I think we didn't mess up with anything wrong, so we should be fine. Let me just cancel this. I think 6 maybe is a lot. Yeah, I think 4 is better for my system. Because when you are using Windows subsystem, you cannot actually use all of your capability. There are some number of processors which will be assigned to your system, and that is different maybe with your capability. So hopefully after an increment, I will just kill it. I was just to show what would be the microstructure and compare it to the one which has been generated by Dream3D to show that the microstructure will match 1-to-1. So before that, let me go over the periodic. So before I start the periodic boundary condition, is there any question regarding the parts that I've covered so far? Could you elaborate dislocation-based constitutive laws in CPFE model? Yes, you can. Actually, one of the Audi, who is a co-developer of the code, is implementing a dislocation-based model within the code. So hopefully he will, our estimation is by the end of the year, we have at least the first draft of the model. So Adi, if you want to explain more, you can.
Yeah. So, I mean, basically, what I'm trying to do is implement a dislocation-based constitutive model that includes the effects of both, like statistically stored and geometrically necessary dislocations. So there will be something like a Cox making law for the statistically stored dislocations, whereas for the geometrically necessary dislocations, it will be computed. Indirectly from, or rather directly from the kinematic incompatibility tensor. So it's based on I think Arsene Liss and Park's work in the 1999 paper. So I'm currently working on that, and hopefully, we can get it, or at least there'll be an implementation ready by the end of the month, and then there'll be the testing phase where we'll actually test it on different microstructures to see how it performs. Yeah, so we are actively working on that part. Thanks for mentioning it.
Thanks, Adi. So yep, that would be another interesting output you can use. How do you handle hardening on different slip system in HCP and BCC structure? So if you have HCP or BCC and you have different hardening, you can assign different hardening parameters for them. For example, if you open one of the applications of HCP, oh, sorry. Here, you can see there are different CRSS for different slip system. The order is important. Whatever order you're doing here for basal, prismatic, pyramidal, whatever order you're using, you should keep the same order in your twin direction and slip direction. Like you have another file which is slip direction So these are the 18 slip system you're using: basal, prismatic, pyramidal A, and pyramidal A plus C. So you need to keep the same order. But the hardening can be also different for each system. And the latent hardening.txt, which will be a matrix, which define the latent hardening. And it could be, unlike many programs that just allow you to change one number or two number for coplanar and planar, we give you the flexibility to change the numbers for all of them, which in this case, it's unit. I think, yep, that's it. Was it the answer of your question, or I should elaborate on that? Okay, thanks. So I think we got the visualization. So we can open this. So this is the Dream3D one. So I will open the results from the simulation. Oh, sorry. Application, FCC random rate dependent. Results, projects. And I will do this. Grain ID. So this is, I click on this. Okay, now I can actually look, you can look at this one, and then I will, yeah, it's pretty much the same. So you can see that the PRISMS-Plasticity actually generate the same macrostructure, which we expected because we used 32 by 32 by 32 for FE mesh, and we had the initial macrostructure of 32 by 32 by 32. So we should precisely capture the Dream3D macrostructure. But yeah, that's it. So let's move on with the periodic boundary condition. So periodic boundary condition, this is very interesting. It seems easy, but the implementation of this periodic boundary condition, it took us a lot of time. So an important thing is, first, the generated macrostructure, it should be recommended to be periodic. We had analyzed the sample, which it actually doesn't have the periodic macrostructure. So the result would be slightly different. So that would matter, the periodicity in the macrostructure. Another thing is, if you are using periodic boundary condition feature, you cannot use set refine factor. For the more detail, whatever I'm explaining, you might not understand fully today because there are a lot into that. And even for me, it took a lot of time to take a good grasp on the concepts of how it works. But you can go and check this PhD thesis from Georgia Tech, from Dr. McDowell's group, which essentially this is the type of boundary condition they use in their simulation. And we actually analyze this. You can check one of the papers. I think Chris will do tomorrow in Prisms Fatigue. Maybe he can show the results that actually the periodic boundary condition we are implementing is precisely capture the periodicity in the macrostructure within the mechanical response. So the way we are doing it is we are implementing this periodic boundary condition using a set of linear constraints. So they define initially the boundary condition are defined using three different geometrical degree of freedom collections. So first we have faces without the degree of freedom of edges and vertices. Then we have the degree of freedom on each edge without the degree of freedom for faces and vertices. And finally, we have the vertices as degrees of freedom in all directions. So what we'll have is there is a nomenclature for different vertices, and face nodes. So you can see the explanation here. Node where are this V0, 0, 0? This is the vertices at the X, Y, and Z equal to 0. And for example, FXP is face nodes excluding edges and vertices for surface normal to X axis at X equal to H. In addition to those, we have edges, which are this. So you first need to go and learn what all of this nomenclature mean in the context of the periodic boundary condition. But what you actually will implement in the main input file is you're adding a line set user simple boundary condition false, which means that you're no longer using simple boundary condition. And then you will add set periodic boundary conditions true, which means that you're actually using periodic boundary condition. And there is another file you need to add, which is kind of tricky file, but I will explain. You might actually not need to change it at all in your simulation. So this file is periodic boundary condition constraint file name. It defines all the constraints except the one for applying loads. So periodic boundary condition constraints define all the constraints. So each of those files include the relation and constraints between vertices and edges and faces. And you can see for more information for each of those linear constraints, you can again go to that PhD thesis and read more information. But how it works is the input file, if you open, let me open one of the examples actually, might be interesting. So if you go to application, FCC, periodic boundary condition, and then open, let's say, uniaxial cycling tabular, excuse me. You can see here, user simple boundary condition is false, then use periodic boundary condition is true, and then you have a file. This file is periodic boundary condition constraints. So if you open that, this is a long file. It defines all the constraints you need, but what are each of these numbers mean? So for each of these, you have the vertices part for vertices constraints, you have the edges constraints, and you have the faces constraints. What I mean in the constraints. So if you go to the handout to the page 22, this is a sample constraint I have. For vertices, it's relation between 4 or 5 or 3 vertices. For edges, a relation between a point from edge with another edge and 2 vertices. And for faces, it's a degree of freedom for one face. It's a collection of degree of freedom which are located on the face. And another face and 2 other vertices. So you have generally for edges and faces 4 part within each constraints. And for the vertices, you might have 4, you might have 3. So for vertices, there is another column besides these 4 columns, which defines the number of these items in the linear constraints, this degree of freedom. However, in edges and faces, there is only 4 columns because you always end up with 4 columns. So if you go back to the file, you see in the vertices part, you have 4 and you have 3. So you may have actually linear constraints, which has only 3 degrees of freedom playing in that constraint. So each of these has 2 lines. One is the number for the vertices, like how many degrees of freedom are playing in this linear constraint. The second one is which degree of freedom are actually active on the first line. So for example, number 12 belongs to V110, and 1 defines the degree of freedom along X axis. So if you go back to the handout and you go here, The V000 is know that vertex located at X. Oh, sorry, that wasn't 000. That was 110. So 110 will be node at vertex located at X equal to H, Y equal to H, and Z equal to 0. In our case, it would be X equal to 1, Y equal to 1, and Z equal to 0. So that's how you define the linear constraint. And the second row for each constraint is the coefficient. For example, if you go back to this here, the first one is defining for the vertices, the first column is just a number of this degree of freedom. And the rest is the first line here. It defines which degree of freedom. And the second line defines what are the coefficients. For example, the first one is 1, -1, -1, and +1. So it's 1, -1, -1, +1. So I think someone is not mute. Let me see who is. If you please, I can do that. Actually, it's easier. And if you want to speak, I think let me unmute Adi first. He might want to. Okay. Adi, you can unmute and mute yourself because then you will have, okay. Then you will have the flexibility. Okay, that's good. So this is a little bit maybe overwhelming, but don't worry about it. If you read this handout or the manual, you will get better with this. But the good thing about this is if you are actually having the same periodicity as what we have right now, is you don't have to change this file. For example, the first file is a cube fully periodic, and then you're applying a load in one direction. So for fully periodic, which is a sub-macrostructure, sub-sample, if you're, for example, doing a fatigue application, you can just directly use the file we have here in this folder. So there is no need to change it, actually. But there are some fields you need to change, which are number of vertices constant. So this is still the same. You don't even, so this is if you have fully periodic, and this is if you have two direction periodic and one direction not, which is like thin film. So for thin film, these are the numbers. For fully periodic, these are the numbers. So still you don't have to change any of these. Depending on what condition you're using, you can just select those numbers. This is the part you need to start to change. So this is the part that you're applying the boundary condition. For example, in this case, there are two numbers set. So it depends what degree of freedom are actually active during your loading procedure and how much of deformation you're applying. So if a number on the first row is 1, it means that that degree of freedom will be active. And if a number is 0, it means that that degree of freedom is not. So for example, in this case, we'll have loading along x-axis and uniaxially. And you can see it's 0.5%. This is the displacement that you are applying during the loading time. So it's like applying, if your sample size is, we are assuming it's 1 for now, you can have different numbers, but if it's 1, it's like 5% in tension. This is how it works. This is a little bit tricky, but if you read it more carefully, I'm pretty sure you can get it. Also, you can do tabular periodic boundary conditions. So not only you can do uniaxial, you can then define a displacement table that say, hey, I want to load it first in tension, then in compression, then I want to do another compression, then maybe tension. For example, you can do cyclic using tabular information. For that, you need to make this feature true, set use tabular periodic boundary condition. And then set periodic tabular time equal to 10. And then this means that you will, this is actually your first periodic tabular time. So the first data you have here, it should go there. This is for some internal information. You need to copy and paste it there. And this is your timetable. And this tabular coefficient define if it's plus or minus. So whatever number you want to apply, you put it here. And then you're controlling it using these coefficients. And for example, here the coefficients are, it's kind of a cyclic loading for this case, because it's 1 minus 1, 1 minus 1. So it's a cyclic loading with 5% strain amplitude if the sample size is 1. This will take a little bit for you to digest. That's a lot of information. To be honest, even whenever I'm trying to do another set of simulation, I need to go back and read in more detail all of these parameters. But believe me, you cannot implement it simpler. It's really confusing. So you need to be very careful. But the good news is, for whatever system or loading type, you just need to figure out this once and then you're done. You just need to make sure that you're doing it correct. So what we are doing it is this simulation set is rate independent. So what I will do is I will do change the directory of the folder to FCC periodic boundary condition. That I will do. And then running uniaxial cyclic tabular. And the microstructure is 32 by 32 by 32. You can use either 8 by 8 by 8 or 4 by 4 by 4 just to make the simulation faster. Otherwise, if you have a really strong computer, you can try 32 by 32 by 32. But before going there, this parameter file, if you open it, it's actually designed for a rate independent model. You can change it to rate dependent. It's not hard. But so in this case, what I will do is I will go back to the source. Okay. I will go back to source, material, crystal plasticity, and then, oh, I missed a C. And then I will replace from material models, rate independent. So we have rate independent model, and then copy whatever it has into the folder. Now you should check your calculate plasticity to see, yep, this is the rate independent one. Very good. So I close this, I go back to the applications, crystal plasticity, and then make release to compile, recompile it, and make sure that you're getting the correct calculate plasticity compiled. So we'll be careful if that number will pops up here or not. Okay, so is there any questions so far? I know that you might have tons of questions about this, but I'm recommending you to just put some real time if it's beneficial for you and if you're planning to use periodic boundary condition the way that we're doing. If you have any subsurface material you want to model, it would be very useful for you to study this periodic boundary condition, starting from that thesis and then come back and read the manual and the handout. And then if you have any question regarding that implementation, come back to me and I will be more than happy to figure out the questions. But it's very tricky. It took me a long time to figure those out. So here you can see you calculate plasticity.cc is actually working. It's recompiled. So after the recompiling is finished, then I can go and actually run the simulation. So We'll wait another 50 seconds. Okay. It's almost done. Okay. So I will go to FCC, periodic boundary conditions, and then, okay, then I will need some changes. So I've already put the changes that I want to do here. You need to do the set a skip output equal to 10. You need to put the, oh, I changed the deformation to 0.002. It's equal to 0.2% of strain amplitude for the sample of 1, because I want to have the simulation shorter. And then I put this number here. And lastly, I put the total simulation time 2.2. So this is, this is for rate independent. So, okay, the original plan was, let's modify it for rate dependent. I've just recompiled it for rate independent, the code. I mean, we can do either of them, but since I put it here, okay, I put another slide on how you can actually transfer the rate independent to rate dependent. So you can actually follow this. I will put the recompile here. Let me, that's a good experiment. I can actually try this until it crashes. I have to open another window. Okay. So I will open calculate plasticity, and this is the rate dependence. So I will go back to applications, crystal plasticity. So I will, while I will compiling this again for rate independent. So you need to add this before your elastic constant. So with that, you can actually make your rate independent model rate dependent. So what I did is I've already done that. So I have already done that today earlier, where I was trying to come up with a nice handout for you guys, but this is the application, FCC periodic. So this, okay, application. I will go to test, plasticity, applications, crystal plasticity, FCC, periodic boundary conditions, and I will close this here and then paste it. Okay, now if you open it, you will see all the changes I explained in the handout I implemented here, except I want to go from 8 to 8 by 8 to 4 by 4 by 4 just to make it faster. And it will output every 10 time step, and the results uniaxial cyclic tabular will output the results. So this is for fully periodic sample, and the strain amplitude you're applying is 0.002, which is 0.2%. It's a kind of low cycle fatigue range. And this is a time increment. And this is the material properties for rate and rate dependent that I added to this file before the training started, just keep it consistent. And then, yep, that's it. That's all I need to do right now. Then let's go and see. Yep, calculate plasticity is updated. So I have everything correct here. So I'm just waiting for this. So let me check the grain ID file as well to make sure that the number of headings are correct. So you can see the number of headings are correct, and the voxelize are 32 by 32 by 32, and it's number 5. So that is correct. What else? Sleep direction, we have everything. So we are ready to do the simulation if this one gets done. Okay, that's done. So we go to CD, periodic, and MPI run. Let's do 4 processors. Okay, the name of the file is tabular.prm, and it will start. It should be pretty fast because it's just 4 by 4 by 4. So every 10 time increment, it will output the results for you. And another interesting thing is, if you see here, it will take, so the time step is 0.005. And each half a cycle is 0.2. So it will take 40 time step to reach the first maximum tension, because it starts with 1, the coefficient. So, and this is tensile. So it should go to tension, and tension about 0.2% strain, and then come back and go all the way to minus 0.2%. So that's how I envision the stress strain curve, but let's see how it goes. So the number of increments you want to go all the way is, let's go until here, which is maximum tension, then go all the way to maximum compression, and it goes back to the maximum tension. And the hardening is isotropic. So I expect the loop becomes a little bit larger. So it's not going to be a closed loop. It's not going to be kinematic hardening. So it will take about 200 increments to reach that one full cycle. So 75 of those is finished. So hopefully it will finish soon, the others. And on top of that, there are different type of boundary condition you can actually apply along this periodic boundary condition. You can apply biaxial tension, pure shear, simple shear, uniaxial tension, tabular, and uniaxial cyclic tabular. So if you want to apply any of the boundary condition, which is already here, you don't have to basically change the whole code. You just go and start playing with the numbers here and figure out. So it's a very good way of starting to figure out what are these periodic boundary conditions are. Let's see how many increments did we go. It's 114, so maybe 85 more. So if there is any question regarding what we have here, or any general questions until we get it done, I can answer. Okay, 150. After this, hopefully our final example would be running a sample with our new advanced twin model to just show the twin evolution. We cannot do much with the time that we have. We cannot do a very serious simulation, but we'll try our best to just cover up some of the concepts there and some of the input files to just get you familiar with what's going on within that model and within the simulation. So 25 more time steps and we're done. I'm especially thankful to the people in China. I don't know if any of those are still awake. It should be like 3, 4 a.m. Can we apply multi-axial boundary condition? Yes, you can. It's, yep. Thanks, Chris. So you can see, for example, here is biaxial tension, all the combinations you can use. Okay, let me see if okay, we have passed the 200. So first, let's start with getting the stress strain curve. Okay. So it's application, crystal plasticity, FCC, periodic boundary condition, uniaxial, and then makes it all files. And then go all the way down to the stress strain and then finish. So this is loading along X, as I explained. So you see, it's a little bit hardening happening. It's still 0.2%, maybe not much, but it's happening. So this is about 2%, 0.2%. So it's 0.002 strain, which is 0.2%. So you can see this is cyclic loading basically. And what else you can get out of this? You can, for example, get the evolution of slip activity with the, so this is a cyclic loading. So that's you come up with. And then you can have, something interesting you can come up with is now that you have the output as well, I can actually show you a nice cyclic loading here. So let's go up and open the periodic results, show you the solution, apply, deformation along X. So, okay. Maybe the deformation should be from 0 to 0.002. So this is the first increment, so it's not happening yet, but I will use source filters, wrap by vector, apply, and then use maybe 10. Okay, let's see what will happen. So we're going to marching forward in the time. So it's tension, then it becomes compression, then it becomes another tension. And I can change the scaling to minus 0.2 and then go all the way back and change this to 20. I think this will be really nice. So I can go forward. And I can actually see the projected field as well. So let's go. Oh, I need to rescale it each time. Okay. So let me put maybe stress is about 56. So from 0 to 56, maybe it's a good idea. Or that's a lot. Let's do 30 to 56. Actually, I can see the chart. The stress will be okay. Now I see. Okay. Oh, that's good. You can see unloading, unloading again. Okay. So that's a good demonstration of how this is basically a subsurface periodic boundary condition under cyclic loading. And the results of this simulation will be passed to the PRISMS fatigue. So Chris tomorrow will go over how you can actually use those information to capture the fatigue driving forces out of the simulation. But as a last example, I would like to go over the new twin model and its application. So this twin model can capture both twinning and detwinning, but to do that, we homogenize each integration point to 2 regions of parent grain and twin grain. So there are 4 operations going on: twin nucleation, twin growth, twin shrinkage, and detwinning, which are operation A, B, C, and D. Usually the CRSS and information for operation A is different from B, C, and D, which are the same. So that's the default values we are using. And these operations are using for calculation of twin evolution, which you can read in on many papers. And I think this is basically most of the information you need to see conceptually. The formulations are a little bit complicated, but what's going on is rather having just either twinned or not twinned, we want to have the contribution of both at the same time for each integration point. The implementation was a little bit tricky, but the results came out really well. So the sample that I'm trying to model is exactly the one that we published in 2019. It's an 8x9 by 15 FE cubic mesh, and it has basal, prismatic, pyramidal AC. Back then, I just didn't want to turn off pyramidal A. So what I did is I just chose a really high CRSS for pyramidal A. So I deactivated that way, actually. And to model that, first you need to copy the advanced twin model, calculate plasticity. So what you need to do is you need to go back to source, material, crystal plasticity, and then copy from the material library the rate. Let me see the models. Rate independent advanced twin model. So this is the address is in the handout. So I'm just trying to be lazy. Then I will copy this and paste it here. So if you check the calculate plasticity, it will be the paper that we published in 2019 for advanced twin model. And then there are some questions. Okay, Audi is trying to answer it. That's nice. So you can go back to application, crystal plasticity, and then go to this time HCP and go to advanced twin model cyclic. And now we want to see what are our files now. So besides the sleep direction and sleep normal, you have two other sets, twin normal and twin directions. But there's an interesting idea there. So if you go back to HCP, advanced twin model, and open the PRM file, typically in a regular twin model, you'll end up with 6 extension twinning for magnesium or magnesium alloy. So you will have 6 extra CRSS. But since we have operation A for twin nucleation and operation B, C, and D for twin shrinkage, growth, and detwinning, we'll have 12 CRSS. So besides the information for regular slip system that we have here, and we used to have it in the copper, there is a new section will be added. Set twinning enable true, set advanced twinning model true, which we are using the advanced twin model we develop ourselves in our group. Set twin system 6, what you put the twin system 6, but you can see there are 12 numbers here. The first 6 are operation A, which is usually higher, and the follow-up 6 are operation B, C, and D, which are lower. And then there is twin saturation factor is the maximum twin volume each integration point can get. And this is a twin threshold. So before this twin threshold reached, you have only the parent grain. But we put a small threshold. After that, you have the parent and twin region coexist. So you will get the contribution of both parent and twin. And you have the twin direction and twin normal. For twin direction and twin normal, you don't have 6 anymore. You have 12 because you have operation A and operation B, C, and D. Or no, inside here, you will have 6. But in the code, it will automatically copy this 6. So my bad. So here, because the operation B, C, and D have the same sleep normal and sleep direction for twinning. So you are just need to insert it once here, except for CRSS, since the values are not the same, you need to insert 12 values. For the next step, I will just open the sample, as I mentioned in the handout for the paper, it was 8 by 9 by 15 extruded sample. So it's very suitable for twinning. So what I will do is I will run this sample. And it will, sorry. I need to also update the number of outputs. But since it's 8 by 5 by 15, 8 by 9 by 15, it's like each grain is cubic, so there is not real microstructure. So the only output which is interesting for us is the twin evolution and a stress strain curve. So I will just keep it that way and try to run it. But since the time is very short, I'll try to see, I will just coarsen the mesh in this direction and coarsen the mesh. I think that would be maybe enough. Let's see how fast the simulation is. I think that was wrong. I couldn't, because that's each grain is one. I forgot to compile it, I think, recompile it. Did I? No, I forgot. So that's the reason that, so this was not the problem. So after I update the calculate plasticity, I forgot to recompile it. Let me go back. So I need to recompile it. If there is no change within the file, you don't see any of the changes here except the 50% and 100% for the main files. But since we changed the calculate plasticity, I expect this to come here as 1%. Yep, here. So it's 1% building calculate plasticity.cco. So calculate plasticity now is being updated. So after we get the executive file ready, I can just run the simulation. This will be our, so typically you won't recompile the code unless you're changing your material system or, oh, that's pretty much it. So for every project, you just need to recompile it once and then change with the input file. That's the way we envision the code. But since today is like just training session, I had to go over all these aspects and change the core code itself. So that's the reason we end up with doing recompiling a few times. Okay, hopefully it will be finished in a minute. Okay, now we go to HCP and advanced twin model. And now we are doing this. Okay, that's good. So I just coarsen the mesh in one direction to get the faster results. So hopefully we'll get enough data to have some twin nucleation. And you can see the softening in this curve. So here we are, we are starting from simple compression and then doing cyclic. So we are going to model this part. So you should be able, as the twin nucleation start here, the curves start to soften, like not soften, the curves start to deviate from the linear elastic response. So this is the part hopefully we'll get so far, but we'll see how fast we can get it done. So I can actually go here, copy this, and just name this as 1 and open it here. So this is deformation compression along Z direction. Let's see if it starts to bend. No, not yet. We most probably have a very few integration points start to tween, but let's see how much of it happening here. I don't think it would be even 1%, but yeah, it's very small. So we'll wait a little bit more. Maybe until 100. But meanwhile, if you have any question, I can answer those related to any general questions about prisms or related to the twinning model I just explained. Okay, let's wait until 100. Okay. Let's copy it as two. And hopefully now we have more tween. Yep, now you can see we are almost 0.5%. So if you go and plot the stress along z-axis, it should be some deviation from linear. Yep, you start seeing some deviation from the linear response. So if you can wait for longer simulation or trying to do it longer, you'll get to higher evolution. As you can see in the paper, it went up to a few percent of twin volume, and then detwinning happening, and then another twinning and detwinning. So that's how a brief overview on the CRSS of this advanced twin model. But if you have any like elaborate question about the model, you can shoot me an email or you can just ask now. So with this, let me see the handout. Yep, that's pretty much what I wanted to cover in this training session.